October 1917. The Flanders mud stretched endlessly across what was once farmland, now transformed into a hellscape of waterlogged craters and shattered earth. Near the village of Polkapelle, a British Mark IV tank designated D-51 sat motionless, smoke billowing from its engine compartment. Inside, 6 crewmen choked on acrid fumes as the temperature climbed past 120 degrees Fahrenheit. The engine had seized. Again. Lieutenant James Harrington pressed his face against the viewing slit, watching German machine gun rounds spark off the hull. They were stranded in no man's land, and the enemy knew it. This was supposed to be Britain's secret weapon, the mechanical marvel that would break the stalemate of trench warfare. Instead, it had become a steel coffin. But what happened next, in the desperate weeks that followed, would transform not just the fate of these machines, but the entire nature of armored warfare. This is the story of how a catastrophic failure became Britain's most unlikely triumph. Third Ypres, known to history as Passchendaele, had been grinding forward since July. Field Marshal Douglas Haig believed tanks would provide the decisive advantage. The Mark IV, Britain's latest model, weighed 28 tons and carried either 2 6-pounder guns or machine guns. Its rhomboidal shape could theoretically cross trenches 9 feet wide. On paper, it was formidable. In the Flanders mud, it was dying. By mid-October, the statistics were damning. Of the 76 tanks committed to recent attacks, only 23 had reached their objectives. The others had broken down, ditched in craters, or simply stopped moving. But these weren't combat losses. These were mechanical failures. Something fundamental was wrong. Major Frank Summers of the Royal Tank Corps stood in a forward maintenance area 3 miles behind the lines, staring at yet another disabled Mark IV. The engine block was so hot he couldn't touch it. When his mechanics removed the cowling, they found the radiator completely choked with a paste of mud, oil, and debris. The cooling system had failed catastrophically. This wasn't an isolated incident. Tank after tank showed the same problem. The Flanders offensive had created unique conditions. Artillery bombardment had pulverized the clay soil into a fine powder that, when mixed with autumn rain, became a thick, adhesive sludge. This mud didn't just bog down the tanks. It was being sucked into every opening, every vent, every gap in the machinery. The Mark IV's engine cooling system drew air from outside to cool the radiator. In normal conditions, this worked adequately. In Flanders, it was a fatal design flaw. The air intake pulled in mud particles suspended in the atmosphere. These particles accumulated on the radiator fins, forming an insulating layer that prevented heat dissipation. Within 30 to 45 minutes of operation, engines would overheat, pistons would seize, the tank would stop. For the crews, this meant certain death or capture if it happened in no man's land. Even if they survived, the psychological impact was devastating. These men had been told they were the elite, the future of warfare. Now they felt like they were driving death traps. Captain Robert Hawthorne, a tank commander who had fought at Flers-Courcelette the previous year, wrote in his diary that October, "The men have lost faith in the machines. Yesterday, I watched Corporal Davies weep openly when his tank failed before we even reached the start line. He said he would rather go over the top on foot than trust his life to these metal monsters again. We are failing, and we do not know why. But someone did know why, or at least was beginning to understand." Major Summers had been an automotive engineer in civilian life, working for the Daimler Company in Coventry. He recognized this wasn't a problem that could be solved by standard military maintenance procedures. This required innovation, and it required it immediately. On October 18th, Summers did something unprecedented. He sent an urgent telegram to the War Office requesting permission to bring civilian engineers to the front. Not military personnel, but actual factory mechanics and designers from Britain's motor industry. Men who understood engines not as military equipment, but as machines that could be modified and improved. The request was radical. Civilians in an active combat zone. Unthinkable. But the tank program was in crisis. Without reliable mechanical performance, the entire concept of armored warfare was in jeopardy. Hundreds of tanks were being produced in British factories, but if they couldn't function in battlefield conditions, they were worthless. Within 48 hours, the approval came through. Contact was made with Coventry, Birmingham, and Manchester. The call went out to the motor works. We need your best men. We need them now. And we need them in France. Among those who volunteered was a 42-year-old master mechanic named Thomas Whitfield. He had spent 20 years at the Standard Motor Company, specializing in cooling systems for commercial vehicles. When the telegram arrived at the factory on October 20th, Whitfield was working on a military truck contract. His foreman approached him during the lunch break. "They need someone who understands engines in extreme conditions," the foreman said. "Someone who can think on their feet. It's dangerous, Tom. It's the front lines." Whitfield had 2 sons. One was serving with the artillery in Italy. The other had died at the Somme. He volunteered immediately. By October 23rd, a team of 11 civilian engineers had assembled at a makeshift workshop established in a partially destroyed farm building near Vlamertinge, about 4 miles west of Ypres. They were joined by Royal Tank Corps mechanics and several officers, including Major Summers. The workshop was hardly ideal. The roof leaked. Artillery could be heard constantly in the distance. German shells occasionally fell close enough to rattle the tools on the benches. But they had what they needed most: disabled tanks to examine and the freedom to experiment. The first step was systematic diagnosis. They brought in 5 Mark IV tanks that had failed in recent operations. Each was stripped down, its engine and cooling system examined in minute detail. What they found confirmed Summers' initial assessment, but the problem was worse than expected. The mud wasn't just clogging the radiator. It was being drawn into the engine compartment itself, coating spark plugs, fouling carburetors, and contaminating the oil. The entire air intake system was fundamentally unsuited to the environment. Thomas Whitfield spent an entire day just measuring the particle size of the Flanders mud. He collected samples from different areas, dried them, analyzed their composition. The mud contained clay particles so fine they could remain suspended in the air for extended periods. Any unfiltered air intake would inevitably draw them in. "We need filtration," Whitfield told the assembled team on the evening of October 24th. "But not just a screen or a mesh. We need something that can trap particles this small while still allowing sufficient airflow to cool the engine. The problem is we need it to work in these conditions, and we need it yesterday." The team split into groups. One focused on the radiator itself, examining whether the fin design could be modified to resist clogging. Another looked at the air intake system, exploring ways to filter incoming air. A third group investigated whether the engine compartment could be better sealed to prevent contamination. Resources were scarce. This wasn't a well-equipped factory. They had basic tools, salvaged materials, and whatever could be requisitioned from military supplies. Innovation would have to come from ingenuity, not resources. The breakthrough came from an unexpected source. A young mechanic named Albert Finch, who had worked at a textile mill before joining a Birmingham motor works, suggested using fabric filtration. In the mills, they used cotton filters to trap airborne fibers. Could the same principle work for mud particles? The idea seemed almost absurd. Fabric filters in a tank engine, but Whitfield saw the potential. They began experimenting with different materials. Standard cotton clogged too quickly. Canvas was too restrictive to airflow. Then someone suggested oil-soaked cloth. In some industrial applications, a light coating of oil on fabric could trap particles while maintaining airflow. The oil would catch the particles, preventing them from passing through. They tested it using a salvaged air pump and samples of the Flanders mud. The results were promising. An oil-soaked cotton mesh, layered in a wooden frame, could filter out the fine particles while allowing sufficient air to pass through. But would it work on an actual tank engine under battlefield conditions? On October 27th, they installed a prototype filter system on one of the disabled Mark IV tanks. The filter assembly was mounted ahead of the radiator intake, a wooden frame holding 3 layers of oil-treated cotton mesh. It looked crude, almost primitive, but when they started the engine, the difference was immediate. The engine temperature remained stable. After 30 minutes of operation, the time when most tanks would begin to overheat, the temperature gauge showed normal readings. After an hour, still normal. They ran the engine for 3 hours straight. No overheating, no seizure. When they examined the filter, it was coated with mud, but the radiator behind it was clean. The system worked, but this was only part of the solution. The radiator itself still needed modification. The standard grill design allowed too much debris to enter even with the filter in place. A team led by a Coventry engineer named Harold Mitchell redesigned the grill structure, adding angled louvers that would deflect larger debris while still allowing airflow. They fabricated the new grills from salvaged metal sheets, cutting and bending them by hand. Each grill took 6 hours to make. They needed hundreds. Meanwhile, another problem emerged. The oil-soaked filters worked, but they needed to be cleaned and re-oiled regularly. In battlefield conditions, this would be difficult. How often would they need replacement? How would crews maintain them under fire? The solution was elegant in its simplicity. They designed the filter frames to be quickly removable, held in place by simple clips. A crew could swap out a dirty filter for a clean one in less than 5 minutes. Maintenance crews behind the lines could clean and re-oil the used filters, creating a rotation system. By November 1st, they had a complete solution. New air filters, redesigned radiator grills, and improved engine compartment sealing. But having a solution and implementing it across an entire tank fleet were 2 different challenges. There were over 200 Mark IV tanks in France. Each one needed to be modified. Time was critical. Intelligence reports indicated the Germans were reinforcing their positions. If the British were going to launch another offensive, it needed to happen soon, and it needed to happen with reliable tanks. Major Summers presented the modifications to Tank Corps headquarters on November 2nd. The response was immediate. Implement this across the entire fleet. Whatever resources you need, you'll get them. The workshop at Vlamertinge transformed into a production facility. More civilian engineers arrived from Britain. Military mechanics were reassigned to assist. They worked in shifts, 24 hours a day. The sound of hammering, cutting, and engine testing became constant. Each tank took approximately 8 hours to modify. They could process 3 tanks simultaneously with their available workspace. That meant 9 tanks per day if everything went perfectly. It never went perfectly. Parts broke. Measurements were wrong. Engines that had been sitting idle developed new problems, but they pushed forward. Thomas Whitfield barely slept. He moved from tank to tank, supervising installations, troubleshooting problems, training military mechanics on the new systems. His hands were constantly cut and bruised. His clothes were soaked with oil and mud. He had lost 15 pounds, but he had never felt more purposeful. "This is what engineering is supposed to be," he told Albert Finch one night as they worked by lamplight. "Not just making things that work on a factory floor, but making things that save lives. Every tank we fix is 6 men who might make it home." By November 15th, they had modified 140 tanks. Field tests showed dramatic improvement. Mechanical reliability had jumped from approximately 30% to over 75%. Tanks that previously could operate for less than an hour were now running for 4, 5, even 6 hours without overheating. The crews noticed immediately. Confidence returned. These machines could be trusted, but the real test was coming. British command was planning a major offensive near the town of Cambrai, about 50 miles south of Ypres. Unlike the waterlogged Flanders region, the ground near Cambrai was chalk downland, firmer and better drained. The conditions would be more favorable, but only if the tanks could function reliably. The plan was audacious. Nearly 400 tanks would attack on a 6-mile front, the largest concentration of armored vehicles ever assembled. There would be no preliminary artillery bombardment, preserving the element of surprise and keeping the ground intact. The tanks would lead, crushing through the barbed wire and breaking through the Hindenburg line. Everything depended on mechanical reliability. On the morning of November 20th, 1917, the attack began. At 6:20 a.m., as dawn broke over the frost-covered fields, the tanks rolled forward. The ground rumbled with the sound of engines. For the first time in the war, British armor advanced en masse without breaking down. The German defenders were stunned. The Hindenburg line, considered impregnable, was breached in multiple locations within hours. Tanks that would have stalled and died in previous offensives kept moving, kept fighting. By the end of the first day, British forces had advanced nearly 5 miles, capturing thousands of prisoners and dozens of guns. It was the most successful single-day advance since trench warfare had begun. Church bells rang in London for the first time since 1914. The newspapers proclaimed a great victory. But in a muddy workshop near Vlamertinge, Thomas Whitfield and his team simply felt relief. The modifications had worked. The tanks had performed. Lives had been saved. The strategic impact of Cambrai was ultimately limited. German counterattacks would reclaim much of the lost ground within weeks. But the tactical lesson was undeniable. Tanks could be decisive weapons if they were mechanically reliable. The engineering innovations developed in that desperate October had proven that mechanical problems could be solved, even under the worst conditions. The air filtration system and radiator modifications became standard on all subsequent British tank designs. The lessons learned influenced tank development for decades. The concept of rapid field modification, of bringing civilian expertise to military problems, became an accepted practice. But perhaps the most important impact was psychological. The tank crews had their confidence restored. The Royal Tank Corps had proven its value, and the British military had learned that innovation didn't always come from high-level planning and research facilities. Sometimes it came from desperate men with wrenches and salvaged materials, working in leaking buildings under artillery fire. Thomas Whitfield returned to Coventry in December 1917. He never spoke much about his time in France, even to his family. He went back to work at the Standard Motor Company, designing cooling systems for commercial vehicles. He died in 1943, during another war, never knowing that his innovations had influenced the design of the tanks that would help win that conflict too. The Mark IV tanks, modified in that frantic November, went on to fight in numerous engagements through 1918. Many were eventually destroyed in combat or worn out by use. But the engineering principles developed to save them, the understanding that machines must be adapted to their environment rather than expecting the environment to accommodate the machines, that lesson endured. In the end, the story of the Flanders tank crisis is not really about tanks at all. It's about human ingenuity under pressure. It's about the willingness to abandon conventional thinking when conventional thinking fails. It's about civilian engineers and military mechanics working together, united by a common purpose. And it's about the reality that wars are won not just by courage and strategy, but by the unglamorous work of making things work when everything seems determined to make them fail. The mud of Flanders tried to stop Britain's tanks. For a few weeks in October 1917, it succeeded. But it could not stop the determination of men who refused to accept failure, who saw problems as challenges to be solved rather than obstacles to be endured. That determination, that engineering spirit, proved more powerful than any obstacle nature could create. The breakthrough at Cambrai was celebrated as a military victory, but it was, at its heart, an engineering triumph. And in the history of warfare, those triumphs are often the ones that matter most.